So this lesson is on side angle side and hypotenuse leg. So the idea is if you know that two sides in the included angle of one triangle are congruent to two sides in the included angle of another triangle, then you should be able to prove that these two triangles are congruent by side angle side. So what's really happening here is if we know that line segment AB and DE are congruent, and if we know that BC and EF are congruent, and we know that angle B, the included angle, and angle E, the included angle, are congruent, then we can say that triangle ABC is congruent to triangle DEF, and this is by the side angle side theorem. So here's a simple proof. You're given that KP and A are the same, and you're given that angle PKA and angle RAK are the same. How can you prove that PA line segment is congruent to RK line segment? Again, these should have line segment symbols on them. So we're proving parts congruent, and the only way parts can be congruent is if triangles are congruent. And hopefully you see that when they're talking about angle PKA, and I'm going to highlight that real fast, angle PKA is this guy right here. Well, that can only really be finished as a triangle if you outline that line segment PA. And then the other angle, RAK, which is this angle right here, we would have to kind of finish off that triangle. So hopefully you see the two triangles they want you to prove congruent. So let's see what we can start off with. We know that KP and AR are congruent. We're going to write it in the proof. We know that it's given, and then we're going to mark it in the proof. So KP is here and AR is here. You also know that angle PKA is congruent to angle RAK. That's given as well. Remember, PKA we said was this angle right here. RAK is that angle right there. We happen to have right now a side and an angle. Well, we're looking for something else, and we happen to be in the side angle side lesson, so therefore it must be a third or second side, which would be the third piece of information. Hopefully you realize that we've got an overlap. We've got a shared side, okay, and that's a part of both triangles. So we're going to say the line segment KA is congruent to line segment KA. And the reason for that is because of the reflexive property. Well, now you have your three pieces. So now we have to match up the triangles. Remember, the corresponding letters matter. So I can talk about the yellow triangle. I'm going to call the yellow triangle triangle PKA. And now when I match it up with the green triangle, PKA has to go to triangle RAK. Again, this reason is because of side angle side. Now that you have your congruent triangles, you can talk about all the different corresponding parts that are congruent, but they really just want to talk about line segment PA and line segment RK. And again, once you've got congruent triangles, then the corresponding parts of the congruent triangles are in fact congruent. Let's see if we can get this to one page somehow. Boom, and well, kind of there, I guess. Nope, I don't know if I did that or not. But there's your entire proof on the page. Okay, so let's talk about the second case, which is the HL case. So basically, if you know that the hypotenuse and a leg of a right triangle are congruent to the hypotenuse and the corresponding leg in another right triangle, then you can prove those triangles congruent by HL, by hypotenuse leg. So it's saying to you, okay, well, if we know that angle B and angle E are right angles, and I can mark them as such, and you also know that line segment AB is congruent to line segment DE, and you also know that line segment AC is congruent to line segment DF, then you do in fact have these two triangles congruent. Then triangle BAF must be congruent to triangle EDF by HL. Remember, this does show you the two angles and a side. This is a picture of an SSA triangle, but the fact that you're in a right triangle, that gets overridden, and that's where we get to the HL. Let's take a look at this proof. Alrighty, so, oopsie. We're trying to actually have you do prove that BC is congruent to DC. I tried to cross this out and fix it, and that's okay. But I think hopefully your paper is corrected. This should be actually congruent to DC because we want the corresponding parts to match up. So if we start on with this proof, so if we look at some of the stuff they're talking about, hopefully you see that when they're talking about BC and DC, that they're probably talking about these two little triangles right here. Not so really little, but they're probably talking about this triangle wanting to be proven congruent to this triangle. You can look at the pieces that they give you and hopefully be able to figure that out, or just by looking at the picture figure that out. So the first thing they tell you is that line segment AC is perpendicular to line segment BD. That's given to you. Well, you should know something about perpendicular lines because perpendicular lines form right angles, which means there must be a right angle here and there must be a right angle here. Remember, AC is perpendicular to BD. So we're going to actually write that as our next step, and we're going to say, okay, well, let's name the angle on the left, the yellow triangle angle. Angle ACB must be congruent to the triangle on the right, angle ACD. And the reason here, and I'm not just going to put definition of perpendicular lines, because it's more than that. I'm going to write, you know what? Perpendicular lines form congruent right angles. Okay, so that kind of gets you away from having to say, well, perpendicular lines form a right angle. We're going to say that perpendicular lines form congruent right angles. We now have one part. We also were given that line segment AB is congruent to line segment, this should be 3, not 2, sorry, to line segment AD, and that's given to you. So AB is this guy right here, and AD is this guy right here. Well, we've got right triangles, therefore those must be the hypotenuse, hypoteni, however you want to call it. We need one more piece, and hopefully we realize that there is, in fact, a shared side. So we've got line segment AC congruent to itself. Remember, shared sides are called reflexive. We now have our 3 pieces. It is an angle with 2 sides, but it happens to be in a right triangle. So now we can name those right triangles, and we can say, well, triangle A, and I'm going to go for ACB, is congruent to triangle ACD, and this is because of hypotenuse leg. And then finally, once we've got those triangles congruent, then the parts can be congruent. So finally, line segment BC must be congruent to line segment CD. I keep messing up my numbers here. This should be 6. Because corresponding parts of congruent triangles are in fact congruent. Let's see if we can get this on one page. I don't know why that always makes it go away, but let's see what happens here. There we go. I think that works. I believe there's 2 more examples that we can work on together. Alrighty, so now we've got a couple sets of perpendicular lines. We've got some stuff that bisects some stuff, but we're going for congruent triangles. So let's see what's going to happen here. Statements and reasons. Okay, so AB and BC are perpendicular. AB is perpendicular to BC. That's given. Well, that really just forms one right angle, and that one right angle is right here at angle B. So I'm just going to put that down here as my next thing. So angle B is a right angle. And the reason is because perpendicular lines form right angles. That takes care of this. DE is perpendicular to DC. Well, that ends up being this angle right here, which means step 4 would say, well, then angle D is a right angle. And again, perpendicular lines form right angles. Well, I don't have a congruent statement about those two yet, but aren't all right angles 90? So don't all right angles have to equal one another? So then what I'm going to do now is make that congruent statement about angle B being congruent to angle D. Here's my first time where I see an angle congruence, and that's because all right angles are congruent. It starts talking about something else. It's given AB line segment is congruent to line segment DE. That's given. Where is that located? AB. So that would be here and here. And then it says something else about BD bisecting AE. This line segment, I'm going to kind of outline it for a second. This line segment right here, BD, bisects, cuts in half this guy. So this is the one that's really cut in half, not the yellow. They don't bisect each other. Okay, make sure that that's clear. What's being bisected is AE. So I want to kind of get those right angle pieces back that I happen to erase. And then realize again, let me just kind of bring this up a little bit. So we're using the given that says BD bisects AE. That's given. And because that happens, then BC is congruent to D. Wait, hold on, that's the wrong one. AE gets cut in half. I'm sorry. That means then you can't see the picture. That's why. So AC is then congruent to EC, and that's because definition of a bisector. Let me kind of get back up to the picture. So we've got now this guy, AC, being cut in half. And we should see that we have a right triangle with a hypotenuse and a leg. So we can finally finish this thing up and we can say, all right, well, what they asked me to prove is really in fact true. And then I can say step 9 is, all right, triangle ABC is in fact congruent to triangle EDC. And this is because of hypotenuse leg. Can't see the picture. Let me see if I can get a way to see the picture. Entire page. There we go. Okay. So we had perpendicular lines which form right angles. All right angles are congruent. Then we had some given stuff. So it turns out that this right here, this given was a complete side. And with that bisecting thing, we found out another complete side. And I've got two sides in an angle, but it's in a right triangle, so it's HL. I think there's one more to go. Okay, I'm going to get it back to normal. Alrighty, so we now have HE is congruent to, well, I guess let's back up for a second. We want triangle EFH, which is going to be this guy right here, EFH, congruent to the other triangle, which is GHF. Hopefully you see a shared side. That's probably going to come into handy. I'm going to erase this for now because it talks about perpendicular or parallel lines here. I think that's going to be really important for you guys to see. Erase, erase. Okay. Let's get the first given out of the way. HE is congruent to FG. FG. HE, FG. Then it says that HE happens to be parallel to FG. You need to remember something about parallel lines. Lots of things happen. But if we're dealing with these particular parallel lines, which would be these guys right here, they happen to be cut by one transversal, which is right there. There's more than one, that's true. But this particular transversal that goes across the bottom of it, you've got some alternate interior angles. And to be an AIA, You must be on the opposite sides of the transversal, but touch the parallel line. Same position on opposite sides, okay? So if I take a look here, this angle EHF is going to have to be congruent to this angle GFH. These guys are AIAs. I touch the parallel line and the transversal. Some people want to go out here, but you're drawing an angle that doesn't actually touch a side. Sure, you can extend a side if you want, but that doesn't help you because part of that angle is without or is outside of your figure. So you need to be very careful with parallel lines that you're talking about the right stuff. In this case, the right stuff, those hinged angles, those elbow angles, have to touch the parallel line and the transversal. And those are the ones, the only ones that you can talk about. So we're going to name those. Angle EHF is congruent to GFH. And this reason is because parallel lines form congruent alternate interior angles. Well, we did talk about a shared side already. This happens to be it. So we can now say then HF line segment is congruent to itself. The order does not matter right now. This is reflexive. And we do have an angle sandwiched in between two sides. We do have an SAS triangle, or SAS congruence, I should say. And it is the triangles that they were asking you for. EFH is in fact congruent to triangle GHF because of side angle side. Okay, that's it. So the idea is that when you get to the homework, you're going to be using parallel lines form congruent alternate interior angles, perpendicular lines form congruent right angles. You might be dealing with some segment subtraction or segment addition. You might be dealing with some bisecting. There's a couple different things you're going to be dealing with, okay? So hopefully this is going to be a good start to your homework. Good luck. Good luck.